It's my pleasure to introduce Alexandre Danilenko, now from University of Toruń, but also from the Institute of Low Temperature Physics and Engineering in Kharkov. He will talk about Kazan property T and Haagerup property for locally compact Polish groups via nonsingular Poisson actions of various Krieger type.
Poisson.
Poisson.
Thank you, Artem, for introducing. Thank you for invitation me. It's my pleasure to talk at this seminar. I will talk about Kazan T property and Haagerup property for locally compact Polish groups, and I will use the non-singular Poisson actions in these characterizations. As you can see from the title, the subject of this talk is related to both ergodic theory of non-singular systems and to representation group theory, the theory of group representations.
Yes. No. Try again.
Where is the delay?
So let G denote a locally compact second countable group. Let me remind definition of Kazan property T, Haagerup property. We say that a unitary representation V is of G in a separable Hilbert space H has almost invariant vectors if for every epsilon and every compact subset in G we can find a unit vector C which is almost invariant in this sense. So if we apply Vg to C, then the distance from this vector to original C will be less than epsilon uniformly when G runs K. And the G has Kazan property T if for every unitary representation of G that has almost invariant vector, there is a non-zero invariant vector. Now, a typical example of group with Kazan property T is SL Z when n is greater or equal to 3. G has Haagerup property if there is a unitary representation V with almost invariant vectors and such that V of G goes to 0 as G goes to infinity in the weak operator topology. Typical example of group which is Haagerup, but not, for instance, every amenable group is a Haagerup group. Example of group with Haagerup property which is not amenable is group with free group with two generators for SL2Z.
Is there any relation between Kazan and Haagerup?
Yes, it's written here. Yes. First, every non-compact amenable has Haagerup property. Consider the left regular representation and take a Fellner sequence and consider characteristic functions of these sets Fn. Then they are more and more invariant. Okay, and suppose that we have a group with Haagerup property. Then it has a unitary representation with almost invariant vectors. But if it has property T, then you know there is an invariant vector. But this contradicts to this.
This is not compact.
Yes, not compact, yes, because. for the theory and application of this group, I recommend the following well-known books. The first is about property T, the second is about Haagerup property, which is also called AT mannability. There are many equivalent characterizations for property T, and there is one which is dynamical. Kohn and Weiss proved in 1980 that a group G is non-T if and only if there is a weakly mixing probability preserving G action that is not strongly ergodic. Later I will explain what does it mean, what strong ergodicity is. And there is a similar characterization of Haagerup property. G has Haagerup property if and only if there is a mixing probability preserving G action that is not strongly ergodic. Okay, so you see, I call it dynamical characterization because it uses dynamical systems which are probability preserving. Some weakly mixing probability preserving, and here also mixing probability preserving. On the problem, okay. But so what is the definition? What is the definition of strong ergodicity? I will give it in the general case of non-singular actions. So let S be a non-singular action. We say that a sequence of subsets is S asymptotically invariant if for every compact subset A we have the limit equals 0. So this limit equals 0. Okay. And now S is called strongly ergodic if every S asymptotically invariant sequence is trivial. That is, this holds. Okay, so I think it's clear that if an action is strongly ergodic, then it's ergodic. Indeed, because consider if you have an invariant set B, then consider a sequence B, 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 B. It's asymptotically invariant. Okay, but not every ergodic action is strongly ergodic. For instance, if you have Z action, any ergodic Z action, construct Rocklin tower. You can construct Rocklin tower which occupies as much as you want, for instance, half of the space. And of course, it's very invariant if the number of if the height of the Rocklin tower is very large, yes, exactly. And then of course the Rocklin tower is almost invariant set. Okay. And of course, you can do the same trick with any amenable group. Just construct Rocklin towers and obtain asymptotically invariant subsets. So, a group G, it appears that converse also true. A group G is amenable if and only if every ergodic probability preserving G action is not strongly ergodic.
So sorry, you just said that the Rocklin decomposition holds for amenable groups in general.
Yes, but of course, but in a more difficult way. So one tower is not enough. You need many towers. You have castle of towers, but all of them are sufficiently high, large, and the property of asymptotical invariance hold for them.
Who proved this?
It's Ornstein-Wein's machinery.
Okay.
There is a famous 140 pages paper of Ornstein-Weiss published in Journal Journalist Mathematique. It's from there. And the non-singular G actions of an amenable group are also not strongly ergodic.
So presumably you always assume that you act on a standard space, or?
Everywhere in my talk I consider only standard model space and standard measure. And group is always Polish. All the group considered here are Polish. A group G has property T if and only if each ergodic probability preserving G action is strongly ergodic. I already presented this theorem once. Okay, so you can compare the difference. You see the strong difference between amenability and property T. But if you step into non-singular area, if you consider non-singular G actions, then can be non-strongly ergodic actions for every G in this property. Okay, and it appears recently that there is an analogous characterization of T and Haagerup using infinite measure preserving actions. So Jolly-san proved the following theorem. Group G.
We have a question from online audience. Suhail asks, what happens if G is compact because it is then amenable to test property T?
I consider only non-compact groups to exclude any complications. So G is assumed to be non-compact, locally compact but non-compact. So G is not G if and only if there is an infinite measure preserving G action whose Poisson representation is weakly mixing and admits almost invariant vectors. So you see here nothing is claimed about ergodicity, right? But just infinite measure preserving. But something is said about Poisson representation. Poisson representation is weakly mixing and admits almost invariant vectors. And in a similar way, there is a dynamical characterization using infinite ergodic theory for the Haagerup property. G is Haagerup if and only if there is a zero type infinite measure preserving G action whose Poisson representation admits almost invariant vectors. And again, nothing is claimed about ergodicity here, just infinite measure preserving. This theorem is proved by Danilenko, rather recently.
So what is zero type?
I will give definition. What is zero type? And what is weakly mixing? A unitary representation is called weakly mixing if it has no finite dimensional subrepresentations. Zero type or mixing. Zero type and mixing is just the same for a representation. This means that if you consider U of G, unitary representation is called mixing if UG goes to 0 weakly in the weak topology as G goes to infinity. And okay, this is the definition of the Poisson representation. Given a non-singular action, we can always produce a unitary representation of the acting group in the Hilbert space L2 of the space where S acts by this formula. It's a weakly continuous, and S is called of zero type if US is missing.
Let me ask a question, maybe stupid. UG tends to 0. What is 0? 0 operator?
Zero operator, yes.
0 operator.
Sure. Mm-hmm.
The group, so I think it is identity.
No. In the we consider. Yeah, sure.
Weak.
For instance, if you have any mixing probability preserving action, and you consider Poisson representation not in the entire L2, because then it's no chances to be zero type. But only in the orthocomplement to the constants, then this exactly mixing is equivalent to this property. Okay. And let me say that, of course, zero type and weak mixing of the representation, not confused with the weak mixing of the action, are spectral properties, which means that they are formulated using coupon representations. On the other hand, there are many dynamical properties which are non-spectral. For instance, conservativity, ergodicity, weak mixing. Of course, if you I know that you usually work with the probability preserving action, and then of course then every probability preserving action is conservative, first of all. And of course, ergodicity and weak mixing are spectral properties. But if you step out from probability preserving to general non-singular, then they are no longer spectral. These properties, these properties are no longer spectral. The authors which I mentioned, the Labidge, some, I think they're specialists in group theory, and they just were interested in spectral properties. But for people who work in ergodic theory, of course, dynamical properties such basics as ergodicity and conservativity are very important, but nothing is claimed in the theorems, so I refined the result and I proved that it's possible to choose actions in their theorems which are ergodic and conservative. Okay. Now, so we have several dynamical characterizations of property T and Haagerup. First is using probability preserving action. Second, using infinite measure preserving action. But then what's about non-singular, purely non-singular actions, which do not admit an equivalent invariant measure, neither finite nor sigma finite. So can we prove analogous characterization criterion for T and Haagerup? That's the problem. Okay, but before I state theorems, let me remind some definitions related to non-singular actions. So let S be non-singular G action on a sigma finite standard measure space. S is called totally dissipative if the partition of Z into S orbits is measurable and all the stabilizers, almost all stabilizers, are compact. Or, to put it another way, there is a measurable subset of Z which intersect every S orbit, almost every S orbit, exactly once. And for almost every Z, this subgroup, stabilizer, is compact in G. S is called conservative if there is no any S invariant subset A of positive measure, such that when we restrict our action to this subset A, we obtain a totally dissipative action. So no total dissipativity in any subspace invariant. Then we say that the action is conservative.
So you mentioned before that this is automatic for probability measure preserving
Yes,
actions.
yes.
So
yes.
how do we see it? Is it
It's Poincaré lemma about recurrence. But if the space is infinite, then you can move and never return.
Wandering would be.
Yes, exactly.
On topological.
Or if non-singulars and subsets can squash and more and more and more. And iterations can be non-intersecting, pairwise non-intersecting. So it's wonderful. Okay. Action is called ergodic if there are no invariant subsets except for mu null or mu null. Definition of this is exactly the same as in the classical case. S is called weakly mixing if the Cartesian product with every probability preserved action is ergodic. Of course, we cannot claim product SG cross SG is ergodic, because then there will be no. There are many counterexamples. For every ergodic S, we can find an ergodic action R, which infinite measure preserving, such that their product is not conservative, and of course not ergodic.
So is it the same we can use pointwise spectrum?
No.
Not like
No. It's not spectral problem. Okay. You can ask about L infinity spectrum if it's trivial, but it's also a bit different concept. So another useful concept when you work in the category of non-singular action is Krieger's type. So we say that an ergodic non-singular action T has Krieger's type 2 if there is a measure which is equivalent to the original measure, which is invariant under T and which is finite. There is a finite equivalent invariant measure. If T, then I say that once more. If there is an equivalent invariant measure, we say that T is of type 2. But then type 2 is divided into type 1 and type 2 infinity. If this invariant measure is finite, we say about type 1. If it's sigma finite, we say it about type 2 infinity. If an action is not of type 2, then we say that it is of type 3. This partition into types is very similar to in von Neumann algebras classification of algebras into von Neumann types, also type 2, type 3, and so on. So there is direct correspondence between these types using some cross-product algebra construction. Okay, now about type. Definition, I've already said about this. And now concerning type 3. To define what is type 3 lambda, type 3 is divided into type 3 lambda, where lambda is between 0 and 1. We need to consider the random Nikodym-Coe cycle, rho mu of the action. It is defined in the following way. Rho mu gx. Then a definition of an essential range of a Coe cycle, of the random Nikodym-Coe cycle. An element, so the random Nikodym-Coe cycle takes values in positive reals, multiplicative group of positive reals. We say that an element is an element R of this group is an essential value of the random Nikodym-Coe cycle if for every neighborhood U of this element and every subset A in the space of positive measure, you can find a subspace in A of positive measure and an element G such that the image of B under Tg is still inside A. So we move a part of B inside A in such a way that the Radon-Nikodym co-cycle take values very close to R in the neighborhood. So if you can do this for every subset B, for every subset, sorry, A, then you say that G belongs to the essential range of the co-cycle. Now consider the set of all essential values. Then it's a group. It's a closed subgroup of the multiplicative group R plus star. But this group does not have too many closed subgroups. We know all of them. If it is the maximal possible, so if RT mu, the set of all essential ranges, is the entire group, then we say that T, the action T, is of type 3-1. Is of type 3-1. If there is lambda such that RT mu is cyclic with generator lambda, then T is called of type 3 lambda. And if T is of type 3 but not of type 3 lambda, for lambda strictly between 0 and less or equal to 1, then T is called of type 3 0. So in type 3 0, RT mu is also trivial as in the measure as in case type 2. But in type 2, we have an equivalent invariant measure, but in this case we do not have an equivalent invariant measure in type 3-0.
So what exactly is RT mu in type 3-0?
R is trivial, just one.
Just one.
Of course, it's possible. Some people also define essential value in a similar way, but not only from this group, but at the infinity. So we consider one-point compactification and define essential value not as an element of this group, but plus this one-point infinity. And then 3-0 corresponds when this infinity is an essential value. In type 2, there is no infinity in the group of essential values. Two non-singular actions are called orbit equivalent if there are subsets, canal subsets of a full measure and an isomorphism between them, such that pair y prime belong to S orbit equivalence relation is and only if phi y belongs to the R orbit equivalence relation. So orbits goes to orbits. It's a very weak equivalence relation. For instance, if you consider only finite measure preserving actions, then and consider only amenable groups, then all of them are orbit equivalent. Okay, but if the actions are just non-singular, then we have lots of possibilities. But Krieger's types is an invariant of the orbit equivalence. So now let me state the main results. Let K be a Krieger type with 3 lambda, when lambda is between 0 and 1 or to infinity. Then the following are equivalent. G does not have the Kazhdan property P. There is a weakly mixing non-singular Poisson G action T star of Krieger's type K with extra properties. the action is essentially free, non-strong ergodic, and IDPFT. I will explain later what does it mean. IDPFT implies that the T star is amenable in the Greenleaf sense. Hence, it is amenable in usual Zimmer sense if and only if G is amenable. Moreover, if T star is of type to infinity, then there is a T star Fellner sequence of subsets of measure 1 in the space with respect to an equivalent invariant measure, sigma phi. And theorem B. It looks almost exactly like the previous theorem, with the only difference that there is a weakly mixing zero type. So this is the only difference from the previous theorem. In addition to the properties, there is a weakly mixing action of zero type. So now let me explain all the concepts that you used during in the statement of theorems A and B. So let T be a non-singular G action on a standard probability space. Lambda G is the left Haagerup measure on G. T is called amenable in the sense of Zimmer if there is a G invariant mean from algebra L infinity xg onto L infinity x, where xg is furnished with the diagonal G action. We have an action on x, and on G we consider usual action by left rotation. T is called amenable in the Greenleaf sense if there is a G invariant mean on N infinity x. So if we consider if x is group itself and action is just by left rotation, then we see that amenability in the Greenleaf sense is exactly the concept of amenability of a group. Of course, each probability preserving action is already amenable in the Greenleaf sense. Consider integral. Then this is an invariant G. Now, definition, weak containment for unitary representation. What does it mean? Suppose we have two unitary representations, P1 and P2 of group G in different Hilbert spaces, doesn't matter, might be different, H1 and A2. We say that P1 is weakly contained in P2 if the following holds. So we take vector from the Hilbert space and consider the following function on the group G. And then consider similar function generated by the second representation. So if every function from the first representation can be approximated uniformly on compacts by linear combination of these functions of the second representation, then we say that P1 is weakly contained in P2. Denote by LG the left regular representation of G in L2, and by EG the trivial representation of G. Now, for non-singular G action T, we have the following. If G is amenable, then T is amenable. But the converse is not true. If T is amenable, then the coupon representation is weakly contained in the left regular representation. The converse is not true. If UT has almost invariant vectors, if and only if identical representation is weakly contained in the coupon representation. T is amenable if and only if identity representation is weakly contained in the unitary, in the left regular representation. T is amenable in the Greenleaf sense, if and only if identity is weakly contained in the unitary, in the Koopman representation. And finally, if T is amenable in both senses, in Zimmer sense and Greenleaf sense, it follows that G is amenable. Oh, it's easy to deduce from if T is amenable in the Greenleaf sense, then trivial representations is weakly contained in UT. But because T is amenable, UT is weakly contained in LG. So we obtain that identity representation is weakly contained in LG, which means that G is amenable.
So, about the fact that if you have an action that is Zimmer amenable, it's not equivalent to this fact that the Koopman is weakly contained. I only know one example of this. Do you know if there are some people who found examples?
You want an example
for representations which give actions which give a Koopman which are weakly contained in the regular but are not Zimmer amenable.
For non-amenable group, amenable action for non-amenable group, it's easy. For every locally compact group, we can construct, for every locally compact Polish group, we can construct amenable action, which is non-singular.
No, my question is the following. An action such that the Koopman representation is weakly contained in the regular, but it's not amenable. So the converse is not true, you see. And this is true. But I only know one example that was given by Krieger and Tamara de la Roche. And I would like to know if there are others, if you know. Because I would like to understand this difference. No, okay, thanks.
Let's go further. Next, definition of non-singular Poisson actions. So, suppose we have a standard Borel space and an infinite sigma finite non-atomic measure on X. Denote by X star the set of all purely atomic Z plus valued measures on X. For each subset A of positive but finite measure mu, you can define a mapping NA, just like that. Measure of the set. And denote by B star the smallest sigma algebra on X star such that all the mapping Ni are B star measurable. Then there is a unique probability measure. So we started with sigma finite infinite measure, but now there is a unique probability measure on U space satisfying the following two conditions. This measure has a Poisson distribution with parameter mu A for each A, subset A of a finite positive measure. And if you have a finite family of mutually disjoint subsets A1 and Q of finite positive measures, then the corresponding random variables n A1 and AQ defined on this space are independent. This is a classical definition of Poisson suspension of the space. So we started with infinite space x b mu and obtain a finite measure space x star b star mu star. Now, if we have an action, we want also to introduce the following group out one. Consider all non-singular transformations which are rather close to measure preserving. In the following sense, their Radon-Nikodym derivative is close to 1, up to function from L1. Then it's a subgroup, and it appears that if we have an action Tg, not singular G action, such that every transformation belongs to this subgroup out1 x mu, then the corresponding corresponding transformation TG star, defined in such a way, will be non-singular. If TG belongs to out 1, then TG star will be non-singular in this new space, in the Poisson suspension. So, if we just given a non-singular transformation and we consider T star defined by this formula, then you get sometimes a singular transformation, which is not interesting. We are interested in non-singular. So if you want to get a non-singular, you should input some restrictions. So the transformations should be almost in some sense preserving measure. For instance, from out 1. Okay. So given an action of inside out 1, we obtain an action on this Poisson suspension. And this action, new action, T star, is called the Poisson suspension of the original action T. We can easily calculate the random-Nikodym derivative of this new action. So it is defined on the space X star. So what is X star? You can think that every point is a configuration. So it's countably many points from the original space. So omega consists of countably many points. So you should take all these points, countably many, and calculate the random-Nikodym derivative of the original transformation, d mu, dg, d mu, at these points. And then multiply all of them, countably many. And it appears that this infinite product converges. And it converges in absolute way, so you can change the order, the value will not change. So this is well defined. And this of course well defined because we know that our TG is from L1, from out 1, which means exactly that this function is integrable. So everything is well defined, so this is exactly the random-Nikodym derivative. In particular, if T preserves mu, then T star preserves mu star. Indeed, here everything is 1, 1, 1, 1, so the product is 1. And here is also 1, so this is 0. This is 1, so the random-Nikodym derivative is 1. So I'm afraid I ran out of time.
It's a 15 minutes.
1 second.
16.
And very important property of Poisson suspensions is that if we partition X into invariant subsets, T-invariant subsets, then Xn, then X star, mu star, T star, is canonically isomorphic to the infinite product of X n star, mu n star, T n star. So the dynamical system X star and mu star T star is called the non-singular Poisson suspension of this system. Problem, do they exist? So are there really non-singular ergodic Poisson suspensions? Can we obtain a Poisson suspension non-singular which is not of type 2-1? So it does not admit an equivalent invariant measure. And we showed, yes, if G is countable amino, and the next question, if yes, then what is Krieger type, possible Krieger type for non-singular Poisson suspensions? In case when G is countable amenable, then in my joint work with Kozlov, we showed that every Krieger type can occur. So for every Krieger type, we can construct non-singular Poisson suspensions, which is ergodic and this Krieger. But for countable amenable. So what's about non-amenable groups? We also need consider a new class of systems which we call IDPFT, infinite direct product of finite types. What does it mean? Of course, in robotic theory, you often consider systems which are infinite product of many systems, countable many. But if you have non-singular systems and you consider direct product of countable many of them, then you can obtain a system which is not non-singular. So, but sometimes it will be non-singular, and we know exactly when if we apply Kakutani's theorem about equivalence of product measures. So, suppose, yes, we have a sequence of probability preserving dynamical systems, Zn, nu n, Sn. Sn is an action here, which is nu n preserving. And then let us change every nu n with a new measure, mu n, which is equivalent. Nu n we replace with mu n in such a way that the infinite direct product is mu non-singular. Then, if this holds, if this is really non-singular, we call that this system is IDPFT. IDP, infinite direct product of finite types. Well, it's easy to calculate the Radon-Nikodym derivative. And why it's interesting? Because whenever we know that every multiplier here is mixing, and the whole system is mixing with respect to mu n, and this system, IDPFT, is conservative with respect to mu, then with respect to mu, it's weakly mixing. So conservativity implies ergodicity and more with mixing. Okay, and there is something like directional version of this theorem. And if T is IDPFT, then T is amenable in the Greenleaf sense. Well, now I repeat main theorem, because now you already know all the concepts. So
can I ask a question, because I'm a little bit confused. So your IDPFT actions,
yes.
so they are your reference measure. It's a probability measure, right? Because it's like a tensor product of probability
IDPFT,
measures.
yes, it's a probability measure always. Yes, that's true. That's true. And Poisson suspensions are also defined on space with probability measure. Theorem B. Just the same as theorem A, but with zero type.
Sorry, to clarify, so when you write hence T star is minimal, so this is under assumption that either of the assumption is true? When you write hence.
This is a characterization of Haagerup property. G is Haagerup. If and only if, so we have very many criterion of Haagerup property. For every k, you have an equivalence. K is equivalent to existence of action, G action free, of zero type, and with many other properties.
I mean,
if you have amenability in the Greenleaf sense and amenability in singular sense, you has amenability of the group. This is what it is.
So can I ask one more question? So coming back to so you have a construction of this T star,
Yes.
of Poisson type, and I think about this T star as kind of being upstairs, coming from some transformation below.
Yes, sure, always.
And now you're saying that this T star has a product structure.
Exactly.
But does it mean that if this T star has a product structure, does it also mean in practice from the construction that this thing downstairs also was a product?
Downstairs, no product, they are union of
Right, okay, but
disjoint copies.
right.
And in every copy you have action here, then you unify with this, and then you lift, consider suspension Poisson, and you'll get infinite product structure.
But this is the result of this type. I have a Poisson action which is IDPFT.
Yes.
then it must imply.
No.
Okay. So this is how you construct
Sure,
it.
sure.
Right.
Of course.
There's
No. And here exactly, I explain how to construct this. So we start with many copies. We start with an action, with some properties which is infinite measure preserving, and we know that it existed due to some previous papers. And then we consider infinitely many copies of this action. And then on every such copy, we change the infinite invariant measure a little bit on a subset of finite measure. And then we choose in the right way these constant parameters to achieve all necessary conditions, and we can control ergodicity. And no, we cannot control ergodicity because it's the most difficult property. We can control conservativity, but because we have IDPFT and we know conservativity, it applies with mixing. So the most difficult is to control Krieger's type, and in every case, 3-0, 3-lambda, 3-1 to infinity, you apply a bit different technique, but everything is controllable using these parameters. So once more, I start with the measure preserving G action on infinite sigma finite standard measure space, and then we change measure. We consider countable many copies of it. Mu n is an invariant measure, proportional to the original kappa. But mu n is different, a little bit different from mu n. Look at the density mu n with respect to mu n. This is Fn. Fn is such a function. This function is 1 everywhere out of Fn. And on Fn, on subset Fn, it is exactly lambda n. That's okay. Let me stop here.
Questions?
So let me ask this question. So this result that you present here, I mean, you have the characterization of Haagerup or non-T via the existence of an action.
Yes.
There are results, like Jolisson and also some other people, which tell you that, say, you have Haagerup property even only if a typical action has certain properties. So you look at, say, all measure preserving actions on 0, 1, and you say that there's a dense G delta section, set of actions with these properties. So the first question would be, so, okay, so if you take your class of Poisson actions or whatnot, so can you still topologize it in a natural way? Is there still a kind of natural notion of?
Sure. There is of course topology, natural topology, Polish topology on group out 1. It's mu. Okay. We will consider individual transformation. Yes. So whenever T is from here, this guy is well defined. Poisson suspensions. Sure. Poisson suspension of T. So typically, there is natural topology here.
Okay.
Natural Polish topology. D1. So what is typical? Typical situation is that T is of type 2-1, but not in this group, in subgroup. So this group, in a sense, is a semi-direct product. Of this group and R. So we consider this subgroup.
Okay. Okay,
So typically, an element is of type 3-1, and this guy at the same time is also of type 3-1.
Okay. And then could you have a result like this, that if you have Haagerup property, then a typical type 3-1 transformation would have the properties you want?
You say about transformations or action, or groups, because Haagerup is not as, but you mean typical,
So you
in
keep a group. So
Keep
this
a
is the
group.
result of Joly-Sound. You keep a group. Say a discrete group. I only know discrete groups. A discrete group. And this discrete group, you can look at all actions of this fixed discrete group. Again, talk about measure preserving. On 0, 1. Right? And this is a result. The group is Haagerup, even only if you have a dense G delta set of actions which have these nice properties. So a priori the definition is only there exists one. In the same way there's something that it actually goes back in a way to Bergelson and Rosenblatt, the typical representation.
Yes, they have something for representations, but not for, it seems to me, not for group actions.
So that, but that was done by Joly-Sound later. So there's a paper, I think actually it's fundamental.
Really?
Yeah.
I don't know about this paper. So.
Okay.
Interesting.
Because that would be a question whether in
Yeah,
this
sure.
you can also, because this is kind of, it's actually not too difficult, but okay, I mean, you just have to do a little bit of work. It's a certain stability.
Any other questions? Maybe online audience? If not, let us thank Sasha again. And we will resume in about 16-17 minutes.
Can you